Hey guys, I have your notes here for section 5.1, and this is a fairly complicated section. Obviously, we're spending 3 days on it, so it's going to take us a while to get through it. We're giving you plenty of time by spreading it over 3 days. Plenty of time to practice and kind of get used to trying everything that could possibly come up in these types of problems, okay? So what I need you to do is keep up. So what's going to happen is on the 5.1 day 1 video, that's this one, I'm going to give you an overview of what you're doing, tell you what you can and can't do while you're working these types of problems, give you some tips on how to get started, and we'll go through a few examples of the easier types of problems. So the day 1 will probably be a pretty lengthy video. Day 2, you'll watch day 2 after you've completed day 1 homework, or at least done most of it. So you've watched the video, you've taken the notes, you've done day 1 homework, you're kind of starting to get the hang of it. Okay, so day 2, I'm going to do some harder examples with you. So I've already taught you everything. I'm just going to do some examples, give you new ideas of new things to try as you're working through these types of problems. So the videos, same thing for day 3. You've learned everything. I'll just give you a few new techniques to use on day 3 homework. So the videos for days 2 and 3 should be shorter. But this one, I don't know, no promises on how quick I can get through all this. So what I'd like you to do first is on the page where all of the tables are, we're gonna use this page. You're gonna have this piece of paper in front of you as we're working through the examples today, and the next day, and the next day. So make sure this is good, clean, legible. You're gonna use it quite a bit. We have 3 different types of identities. We have reciprocal, quotient, and Pythagorean, and those are all listed down the side of the page. What I need you to do is probably pause the video and copy all of these trig identities. Now, the reason I want you to copy them instead of me going ahead and writing them in before photocopying them and passing them out to all of you, they're going to have to be memorized. So you copying them down is a good start as you're on your way to memorization. And don't worry, again, I'll give you tricks on how to memorize all of these. But just go ahead, pause the video for just a minute and copy those down. Alrighty, you all know that sine and cosecant are basically upside down fractions from each other. So what we've done is we often, up to this point, we found a sine fraction and we turned it upside down and we got our cosecant fraction. Now, anytime you see anytime you see 1 over cosecant, I want you to think, oh, I really don't like working with 1 over cosecant. I'm going to turn that into sine. And that's a valid substitution you could make. If you see this in any of your problems in the next couple days, you can pull this out of your problem and substitute sine in its place. Okay? Same thing for 1 over secant. You can sub in cosine. And when you see 1 over tangent, 1 over cotangent, you can sub in tangent. Also, when you see just a normal cosecant, you can sub in 1 over sine. Why would you do that? Why would you make something like this a little more complicated and turn it into a fraction? Because you're better with sines and cosines than you are with cosecants. If you see a secant, you can turn it into 1 over cosine. If you see a cotangent, you can turn it into 1 over tangent. Or, here's a couple more options for you. For tangent and cotangent, you can turn tangent into sine over cosine. Or, you can turn cotangent into, since this is the upside down version of tangent, let's turn this one upside down. So cotangent is cosine over sine. Now, below we've got these Pythagorean identities. I know, these look intimidating, but, and honestly, I have this one memorized. I got it. I can quickly come up with these two knowing that one. And I'm really good at that one. I've got that one memorized. I can come up with that one pretty quickly. These two follow it. In fact, well, I'll talk about that in a minute. And honestly, I don't have any of the other ones of these memorized. I don't. And I'll show you how I come up with them each time I need them. So if I were getting ready to do a homework on this or take a test on this, I would, from here, come up with all the other ones that I need. And I'll show you how to do that. First, I want to show you where the first one comes from. Let's say you have a point on the unit circle, okay? So this is on the unit circle. It's a point. I'm calling it x comma y. You okay with that? X comma y. That's this point. Unit circle, so the radius is 1, aka the hypotenuse of this triangle is 1. It's the unit circle. That's what happens on the unit circle. Remember on the unit circle, well, hang on, I'll get there in a minute. So, right triangle, here's theta. I can say in this right triangle, leg squared plus leg squared equals hypotenuse squared. So I can make this equation, leg squared plus leg squared equals hypotenuse squared. Now, do you remember on the unit circle how, only on the unit circle, your cosine is your x value and your sine is your y value? Remember that? So, since we're on the unit circle, I can sub in cosine for my x value. I can sub in sine for my y value. Okay? And you're going to see this all the time. This quantity squared is the same as putting a 2 on the cosine abbreviation. Writing it this way allows you to write it a little bit more quickly because you don't have to use the parentheses. However, writing it this way is wrong. Very, 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 very wrong. This right here represents some cosine fraction squared. Right? What are cosine fractions? Isn't a common cosine fraction 1/2? This represents the fraction 1/2 squared, or 1/4. This represents the same thing. This is squaring the fraction, not the angle. These two represent the same thing. This says whatever your angle is, like, I don't know, 60 degrees? Whatever your angle is, square it. Really? You want me to take a 60-degree angle and multiply it by another 60-degree angle, and then you want me to do cosine on a 3,600-degree angle? That is so wrong. So you may not write it like this. If you want to not use the parentheses as you're writing because it takes extra time, it's extra work you have to do with your pencil, oh, my fingers get so tired, then this is the way you have to write it, not like this, okay? All right. So, there we go. Because of the unit circle and the relationship that x and y have, and because that x is cosine and the y is sine, we now have cosine squared plus sine squared equals 1. There you go. That's our first Pythagorean identity. You have to memorize that. First identity. Sine squared plus cosine squared equals 1. Now, the next two just come from manipulating that equation. So let's say that I take this equation and I subtract cosine squared from each side. Subtract cosine squared from each side, and I get sine squared equals 1 minus cosine squared. Or start over. Come back up here. Sine squared plus cosine squared equals 1. What happens if I subtract sine squared from each side? Subtract this from each side, I get cosine squared equals 1 minus sine squared. See? These two just come from manipulating that. So do you need to memorize those two? No, not really. Do you need to memorize that one? Absolutely, 100% you need to memorize that one. Now let me show you how the other two come about. So I've got cosine squared plus sine squared equals 1. If I decide to, now think about this. Think about this. This one involves tangent squared. So what if, to get a tangent, what if I tried to divide this term by cosine squared of theta? Is that legal? Well, simply dividing that term by cosine squared is not legal. Now, sine squared divided by cosine squared does give me tangent squared, but if I'm going to divide this by cosine squared, I have to divide everything by cosine squared. So I'll do that one. I'll do that one. And I'll do that one. Okay? So over here I've got cosine squared over cosine squared. Those cancel. And when they cancel, I'm left with 1 plus sine squared over cosine squared, that is a tangent and another tangent, so that's tangent squared. And then 1 over cosine squared is a cosine secant squared. There you go. See that one? 1 plus tangent squared equals secant squared. 1 plus tangent squared equals secant squared. How did I get that? I divided everything on here by cosine squared. Okay, now I've got it written again. Let's do this again. So same equation. Last time I divided by cosine squared. This time let's divide by sine squared. Sine squared over sine squared cancels. That's a 1. Cosine squared over sine squared, cotangent squared. It's up in that table. And 1 over sine squared, let's see, 1 over sine is cosecant. Cosecant squared. There you go. Cotangent squared plus 1 equals cosecant. Cotangent squared plus 1 equals cosecant. And again, the ones underneath it just come from manipulating. So here we subtracted 1 from both sides. That's what it would look like. Here we subtracted, let's see, we went back up here to the original. We subtracted tangent from both sides. So these two lines are just manipulations of that equation. And where did this equation come from? The top equations came from this one. First time around, or whatever, divide by cosine squared, divide by sine squared, and you'll come up with those other two. So that one has to be memorized. All right. Now, as I've shown you, these up here all work when they're squared. So I turned, what did I do? I turned 1 over sine squared into cosecant squared. So make yourself a note that the first two sets all work when they're squared. Example. 1 over sine squared is equal to cosecant squared. All of those work when they are squared. However, the ones down here, the Pythagorean identities, these do not work unsquared. Make a note of that. Don't ever, ever, ever allow yourself to make any of those substitutions if they're not all squared. So if you see sine of theta plus cosine of theta, do not say, oh, look, sine of theta plus cosine theta, that's just 1. No, it's not. Not at all. Not at all. They both have to be squared. Okay, we good? Do not lose this paper. Pretty much, this all has to be memorized. But, I mean, I think you already know it. You already know that sine is the upside down version of cosecant. So you already know all these. You already know that tangent is sine over cosine. You already know that. The only one that you're going to need to work on memorizing is this one here, sine squared plus cosine squared equals 1, and coming up with those two. Because none of these will be given to you on a test. So you're going to have to know this one, and you're going to have to be able to either know these or come up with them. I would be the person that as soon as I got my test, I would write this one down, the first one, I know it, sine squared plus cosine squared equals 1. I would do my little divisions really quickly, and then I would write the other two out on my paper to have them, if I needed them, on my test. All right, so keep that paper handy. Before we get started with these, I've got this paper. It's legal versus illegal. And you all are going to make so many illegal algebra mistakes. It's going to be unbelievable. You're going to think that you were pretty good at algebra, and now all of a sudden, whew, where'd it go? Those skills just totally went out the window. So, first one, when you have a fraction and you've got a binomial on top and a monomial on the bottom, it is okay to split that fraction into two fractions. You can put this over the 2 and the 7 over the 2. It is legal. Why is that legal? Think about it backwards. Think about it backwards. This plus this, two fractions. Do they have a common denominator? Yes. How do you add fractions? You add the numerators, but you don't add the denominator. That's totally legal. This, completely illegal. If I've got 2 down here, I can't split it. I can't put the 3 over the 4 and the 3 over the x and call those two equal. Why not? Think about it backwards. If you look at this backwards, this is a fraction, this is a fraction. If I wanted you to add them together, what would you have to do first? You would have to get a common denominator. Right? You don't just stick these two down there and add them together. Good heavens, no. Okay? So that step's illegal. All right. Remember when you square a binomial, two terms separated with addition or subtraction, when you square a binomial, you have to FOIL it. You can't just drop the 2 on the x and drop the squared on the 3. That's illegal. This one is factorable. This is called a difference of perfect squares. It factors x plus 4, x minus 4, because the outer and the inner would cancel each other out, and you're left with x squared, and you're left with negative 16. X squared plus 16 is not factorable. You can't do that. Because if you FOILed this, you would have a middle term. If you FOILed this, you would have a middle term. This is not factorable. When you're rooting a monomial, these are all held together with multiplication glue. You can square each piece. You can square the 4 and you can square the x squared. That's legal. This is a binomial. This is separated with addition. You cannot square each term. That's completely illegal. When you have, okay, I've got two terms on top, one term on the bottom. I'd be like, oh, I think I want to cancel some x's. This is legal. This term has an x, this term has an x, this term has an x. You may cancel an x. That one crosses out with that one. That one crosses out with that one. And you're left with x squared plus 2. This term has an x. This term does not have an x. I cannot cancel out this x with this. They have to all have an x before you can cancel. This is completely illegal. The 7 didn't have an x to begin with. I've gone over this with you. You can either write it like this, or you can write it like this. You may not write it like this. Absolutely, positively not. I will throw a fit if I see you write that on your paper. Some of you are going to forget that you learned how to divide fractions in elementary school. Now, I don't know what your elementary school teacher told you. I don't know his or her phrasing on dividing fractions. I like same, change, flip. So watch. Fraction divided by fraction. I'm going to go same, change to multiplication, flip upside down. Same, change, flip it, and you get 7 times 9 over x times y. You cannot do same, change, same. This is ridiculous. You know what this is? This is turning a division problem, this divided by this. You just said, you know what, I don't like division. I'm going to pretend that's not division, and I'm going to just call it multiplication because I like multiplication better. So I'm going to take this thing, and instead of dividing them, I'm going to multiply them. No, not legal. You have to flip the second fraction if you want to change it to multiplication. Last one. If this on the bottom is one single fraction, you may do same. Well, I wrote it over 1, but whatever. Same, change. See how I flipped this? One single fraction, I flip it upside down. How about this one? Same, change. What did I do here? Oh, I didn't just do flip. I did same, change, flip. Oh, that's not a thing. Your elementary school teacher never said same, change, flip. She only said same, change, flip. You can flip a fraction. You can't flip. But that's okay, because would you like to turn this into one fraction? Then get a common denominator and add them together. And then you can do same, change, flip. Okay? Same, change, flip. That's a thing. Same, change, flip. Not a thing. Alrighty. Let me kind of give you an overview of what we're getting ready to do, and then I'll come back here to the guidelines. So, here's what it's telling you to do in your notes. Verify the trig identities. Verify is another way to say prove. Okay? An identity. Let me just tell you what an identity is. I think I can do this pretty quickly. Don't copy this down. When you were in Algebra 1, you had to solve things like this. 2x plus 3 equals 2x. Okay, I'll do that. You had to solve things like that when you were in Algebra 1. So you were kind of a newbie at solving equations, so you distributed on the left. You collected like terms on the right. Some of you realized when you got to this point, you're like, wait, something weird just happened. Some of you were clueless and you just kept going. You're like, oh, look, I see, I'm going to get all my x's on one side. So you'd get all your x's on one side, you know. And then all of a sudden you wouldn't have any x's left. And you're left with 6 equals 6. Why, yes it does. Here's what that means. When you got right here, well, anywhere, wherever you got to a point where you could recognize it, it could have been any of these places. But at some point, you got to where the left side was completely equal to the right side, no matter what x was, right? You didn't get an answer here like x equals 4.5. That didn't happen. Why didn't that happen? Why didn't you get a single answer for x? Because this equation is called an identity. It works no matter what you plug in for x. You want to plug in 8? Plug in 8. Both sides are going to be equal. You want to plug in pi? Plug in pi. Both sides are going to be equal. That's an identity. Both sides are equal. Hopefully, you remember that from Algebra 1. So, what we have here, actually, what we have here is a page of identities. These are facts. You know them. You've been using them all along. These work for any value of theta. Don't believe me? This is going to be kind of cool. Pick an angle, any angle. Any angle. Acute, obtuse, negative, I don't care. More than one revolution, I don't care. Pick an angle, any angle. Ready? I'm going to pick, 47 degrees. If I take the sine fraction for 47 degrees and I square it, and I take the cosine fraction for 47 degrees and I square it, guess what I get when I take those and add them together? I get 1. Don't believe me? Pause the video for just a minute, try it on your calculator, but when you type it on your calculator, I want you to type it like this to make sure you're squaring the fraction. So do your cosine of 47 with parentheses and square the whole thing. Do your sine of 47 with parentheses and square the whole thing. You're going to get 1 every single time. So that's a page of identities. Well, on their day 1 notes, there's another page of identities. But you don't know that they're true yet. There's another page of identities, and you don't know that they're true yet. There's another page of identities, and you don't know that they're true yet. We're going to prove that all of those identities are true. So, you don't know yet that the left side truly does equal the right side. That's up to you to prove. Let's prove beyond a shadow of a doubt that the left side truly is equal to the right side. That's what we're trying to do in this whole section. Prove that the left side equals the right side every single time. How do you go about that? Well, you're going to, and I've got these highlighted, these are kind of the things that we're going to do on day 1. These are the ideas that I'm giving you to try on day 1. We're going to start with the more complicated side first. So, number 1, we're going to work with the left side of the equal sign. It's more complicated. Number 2, we're going to start on the left. Number 3, we're going to start on the left. And number 4, we're going to start on the left because it says do that first. We might have to factor. We might have to add fractions. If we add fractions, you might have to get a common denominator. We might use a Pythagorean identity to make a substitution. What's a Pythagorean identity? It's those. We might make a substitution. How can we substitute? Well, here's one thing we could do. If you ever, in the midst of doing these problems, if you ever run across sine squared plus cosine squared, you can pull that out. Guess what you're going to put in its place? A 1. Pythagorean identities for substitutions. All I'll come back to this in a minute. Sometimes you're going to see cosecants and cotangents and secants and bleh. It's just easier to just get everything in terms of sine and cosine. Everything you encounter can be written in terms of sine and cosine. Right? Any of these, how about this? These two can be written in terms of sine and cosine. Tangent can be written in terms of sine and cosine. Cotangent can be written in terms of sine and cosine. It's always an option. Put everything into sine and cosine. Always try something. Keep working at it. If you come to me and say, I don't know what to do on this problem, and you've not done anything, I'm not going to help you. You have to have tried something. Like, look through this list. Did you try this? Well, no, Ms. Neal, because they were already sine and cosine. Okay, I'll buy that. Were there fractions that you could have tried to add together? Could you have tried factoring something? So, make sure you're trying something. And then lastly, the whole thing about a proof is we do not know that the left side equals the right side yet. That's what we're trying to prove. So, you are not allowed to do this. You can't add something to both sides of your equation. Why not? Because you don't know it's an equation. We don't know it's an equation. That's what we're trying to prove. So you can't add something to both sides of your equation. You can't multiply something on both sides. You can't divide something on both sides. You have to work with each side individually. So, this is what I've seen some people do. Some people draw this like line through their equal sign, and that tells them that nothing's allowed to cross over. It's a decent idea. All right? And that's what this pink highlighter says, is you can't do anything to both sides. You can't cross multiply, add or subtract, multiply or divide both sides by anything, because we don't know that the two sides are equal. All right, here we go. Let's try some. Whew. First one, good news. Super, super simple. What are you going to try to do? I don't know. You're going to try to turn everything to sine and cosine. No, it's already there. It's already in sines and cosines. Okay? Oh, how about this? Can you say sine plus cosine squared is 1? No, that one's not squared. You can't do that. Ooh, how about subtract cosine squared from both sides? No, you can't do that because you don't know that that's an equation. So just looking on the left, is there something you can do just on the left side? I think you probably see it. See this term? See this term? How about we collect like terms? Does that sound good? Collect like terms. I get cosine squared, my sines are gone, equals cosine squared. Why, yes it does. We just proved that that's an identity. Yes, they're equal. I proved it. How did I prove it? I just collected my two terms on the left-hand side. Now, that's the easiest one you'll ever do. I don't think any of them are going to be that easy again. Let's try number 2. Looks intimidating. I get it. All these letters in math. Oh my gosh, it looks so intimidating. But we could change everything to sines and cosines. Does that sound like a good place to start? Let's do it. Let's change everything to sines and cosines. So, cosecant. Cosecant I'm going to rewrite as 1 over sine of x. And let's see, I think I'll highlight as I go so that you can see what substitutions I'm making. So I substituted there, minus cosine squared, keep it the same. That's already in terms of cosine. Times, well, here's another one. Here's another cosecant. 1 and that one's already in terms of sine and cosine. So I made 2 substitutions here. How did I know I could make those substitutions? Because it came from this paper. Anytime I see a cosecant, I can turn it into 1 over sine. So I did. Now, that's kind of a standalone fraction. This is multiplication. So cosine squared of x, multiplication, I can consider that over 1, and I'm going to multiply these 2 fractions together. I get 1 over, so that stays there, minus cosine squared over sine. See what I did? I multiplied those 2 fractions together, equals sine of x. I still have work to do. I have to keep working. I have to keep working and keep working until the left side completely 100% matches the right side. So this should dwindle down until it just says sine, because I want it to match the right side. But I just have to do that legally. All right. 2 fractions. It says to minus. Do I have a common denominator? Then minus them. Here's what I get. Put the numerators together. Denominators stay the same. Now what? Well, I'll give you a hint. This is a thing. This is a thing. Find it. 1 minus cosine squared. Find it. What can you put in place of 1 minus cosine squared? Same. Did you find what you could put in there? You should have found that cosine squared, 1 minus cosine, that was sine squared. It's your Pythagorean identity. It was down here, left column, middle row. Okay, we're pretty much there. This is sine times sine. This is just sine. One of these cancels with this one, and I'm left with just sine. So the left, I get this when I cancel. The right was there. I have just proved that this is a true identity. I changed everything to sines and cosines. I used a Pythagorean identity. I did some canceling down here, and I got my left side to match my right side perfectly. Once you get to here, you know you're finished. Number 3. What do you think? How about we change everything to sines and cosines? So I'll change this to 1 over sine. So I made that substitution. Minus, keep the cosine a cosine. Cotangent. What are we going to turn cotangent into? Some people, cotangent. Some people want to turn cotangent into 1 over tangent. That wasn't what I suggested. I suggested, why don't we turn everything into sines and cosines? So why don't we turn our cotangent into this? because it has sines and cosines, right? If I'm turning everything into sines and cosines, I don't think I want to throw a tangent in there. So cosine over sine. Cotangent is cosine over sine. I made that substitution. And then the right side, I'm just going to leave it the same. Okay, that stays the same, minus. Let's go ahead and multiply these two together. So I get cosine squared x over sine of x. Gosh, I feel like I just did this. I did something very similar. Got two fractions. It says to subtract them. I already have a common denominator, so let's subtract them. Combine the numerators. Denominator stays the same. All right, this should look familiar to you. We just made this substitution. You should recognize it more quickly now than you did in the last problem. And that's what's going to happen. The more you do these, the more quickly you're going to recognize all these substitutions that you can make. Okay, so I substituted this for this. And in case you're getting lost, it came from right here. And now I'm going to reduce or cancel or whatever you want to call it. And I've got sine of x on the left, sine of x on the right. And we just proved that that's a true identity. One more. It's getting a pretty long video. Let's do one more. Sure, let's change everything to sines and cosines. So my cotangent became cosine over sine, and you could have done this or you could have not done this. It really doesn't matter. But on the right side, doesn't matter. You could have just said, I am only working on the left. I don't want to work with the right. I don't want to do anything with the right side. You don't have to. In fact, you really don't have to do this. If you do this, that's just a little more writing that you're going to have to do every single line. So, no. You know what? How about we leave it and only change it if we need to? How's that sound? Let's leave it and only change it if you want to or if we need to or whatever. Okay, so I've got sine x plus. I'm going to put that guy over 1. Let's multiply. Multiply. It says multiply. We're not adding or whatever. We're multiplying right now. So I get cosine squared over sine x So from this list up here, what have I done? I have converted everything to sine and cosine. Okay. Use a Pythagorean identity. I can't do that. One of my things is a fraction. I can't do that. Ooh, fraction. I have a fraction. What am I supposed to try to do with fractions? I'm supposed to try to add fractions. How do I add fractions? I get a common denominator. If I want to add these two fractions together, don't I want my denominator to be sine of x? I want this down here to be a sine of x. Okay, multiply top and bottom. by sine of x. So I'm going to multiply sine x. Here's what I get. Now, are you seeing that I'm not multiplying both sides of my equation by sine x? I just multiplied top and bottom of a fraction. That's totally legal. So I've got sine squared on top and just a plain sine on the bottom. Yes? Okay. Common denominator. Woohoo! Combine your fractions together. On top, I get sine squared x plus cosine squared x. Some of you see where this is going. This is a thing. Let's see, I can use blue. This is a thing. You should recognize it. This is a thing. Sine squared plus cosine squared. Pull that out. Put a 1 in its place. Wow, that's a big one. Now, I rewrote this. That became a 1. What about now? You want to change it now? If I change it now, I won't have to do another rewrite, another line. So yeah, you can go ahead and change that now. And I will, for cosecant, I will sub in 1 over sine x. That way they match, and I can call it done. See, I tried to do this early on. I decided, no, I'm not going to do it early on. I'm just going to carry this down, carry it down, and there. Then I changed it. I got them to match. Okay, good luck, guys. Try to get through everything you can. You have me. You have me to like hold your hand through these during class. Or your pre-cal teacher. You have your pre-cal teacher who's just begging you to let them help you. Okay? So, try something, and if you get stuck, ask your teacher. Good luck.